So we're given three regions and a couple of functions, and we want to figure out what the definite integral looks like to calculate the volume of revolution around a given axis. So for instance, R3 around x equals 10. So now this one goes from 0 to 8. So 10 would be the axis out here. Here's our region 3. It's nice and enclosed. And we're going around a vertical axis. So as you can if you can imagine our slice, it's going to be it's going to be horizontal, which means it has a delta y. So we're going to be integrating in terms of y. Now we can see that we're going to have a large radius and a small radius. So if we start to set up our integral, it's going to go from 0 to 2 in the y direction, so that part's pretty clear. Then we'll have a big radius squared minus little radius squared dy. Our big radius is actually just our function here, but we do need to add this extra little bit of space to it, which is 2 units. So our large radius is going to be 4y plus 2, the quantity squared. Our little radius is just this piece here being revolved around this line. It's going to be constant no matter where we are on here, and in fact it's a constant of 2, so minus 2 the quantity squared dy, and there's our first region, or excuse me, our first volume of revolution. Now we're going to rotate R3, same region, around a line y equals 3. So let's just move this down a little bit. Y equals 3 would be a horizontal axis. Let's change colors here. So they'll call that the line y equals 3. We're still revolving the same region. And we have a small radius, and we have a large radius. Check out our large radius. No matter where I look, it doesn't change. We like that because that means our large radius is just going to be a constant. In fact, it's going to be 3 units. So 3 squared, because this is getting revolved around this way. So that's going to get revolved around off the paper there. This one is also going to get revolved around that same way to create the open center. But notice now, this one changes depending on where I'm at, right? If I put the radius here, it's longer. If I put it here, it's shorter. We're going around a horizontal axis, so that means our function is going to be in terms of x. So we do need to solve this guy for x. So y equals x over 4. So our smaller radius is not quite x over 4. X over 4 accounts for this space, x over 4. So our radius, which is this piece, is 3 minus x over 4. So 3 minus x over 4, the quantity squared dx. We've got our limits on x, which will be 0 to 8. So, hopefully you're seeing how we're getting this radius. That's really the key to these volumes of revolution. Last one, R2 around x equals minus 3. I don't quite have room to write this one, but you can imagine it'd be over here somewhere. So pretend that's the line x equals negative 3. So once again, we can see that we're going to be in terms of y. So it's going to go from 0 to 2, because we're going in terms of y. We're revolving R2 this time. So we need our large radius. Again, let's maybe try and switch colors a little bit to make help. Our large radius and our small radius. Those are going to get revolved around to create this thing. Now look, both of them vary this time. And if I do it up here, much larger. So the first one's this linear function. Actually, that shouldn't have gone all the way to there. There's my small. Excuse me. So our larger radius is the linear function, but we do need to add this distance to it because the 4y only gets us from the y-axis over. So we need to add 3 to it. So our large radius is going to be 4y plus 3, the quantity squared. Now we're going to subtract out our smaller radius, which is given by the function y equals x to the 1/3, or x equals y cubed if we solve it the other way. So from here to here is covered by y cubed, because that's the distance from the y-axis. plus the additional 3. So y cubed plus 3 squared dy. And there we have our 3 definite integrals.